Hi, I'm Mariusz Jacyno and welcome to my video blog on Big Data Technologies and Advanced Analytics. In this video, I will show you how you can build a real-time credit scoring application with the use of the latest Apache Spark platform and its streaming and machine learning components. Let's first explain what credit scoring is. In short, credit scoring is a process by means of which we can assess whether a given user is eligible or not for a credit. This process is very important in the financial sector as it allows to mitigate any financial risk associated with credit lending to users that may not be able to pay it. Why having a real-time credit scoring solution is important? Nowadays, the number of online credit applications grows very quickly, and systems that can automatically and accurately perform the credit scoring on big data are in high demand. Unfortunately, building a real-time credit scoring system is not a trivial task, as the overall solution needs to be scalable, reliable, and fault-tolerant. Technically, we could build it around a commonly available math and statistical environment such as R, MATLAB, or any other library. However, this approach would require us to create a lot of custom code to make the solution scalable and reliable. Moreover, we could quickly reach the performance limits of those packages. For example, R can process only data that fits into a single machine's memory. For this reason, in this video, I will focus on big data processing platform Apache Spark that was designed specifically to address all those issues. The key difference it offers is its distributed nature of computations, thanks to which data processing can be performed in parallel on a cluster of computational nodes. Secondly, it can ingest continuous streams of data and has a built-in fault tolerance, and finally it provides its own machine learning library, mlib, that removes the need of integration with external components. This coupling is very important as many iterative machine learning algorithms can benefit from Spark's parallel processing and thus analyze more data at a much quicker pace. For reference, here's a sketch of the system architecture that we will build. Our solution consists of three elements: our credit scoring system in the form of real-time stream processing engine and statistical scoring model, a system that reliably transmits the credit scoring requests to our scoring system, and the final destination system where the output from our scoring system is sent. It is important to note here that requests that are generated and streamed to our system arrive in real time and at high velocity, and the goal of our system is to process them as fast as possible. Before we actually develop the code to handle streaming and processing requests, the first thing we need to do is to teach our system to autonomously assess creditworthiness of users. To achieve this, we will use machine learning library provided by Apache Spark and train a supervised learning classifier algorithm using publicly available credit scoring dataset. Example data provided by this set looks like this and contains all important user features such as occupation, sex, amount of credit, savings, etc., along with the label representing final decision whether the user received the credit or not. For further reference on this dataset, please navigate to the following URL that contains in-depth explanation of all user features included. Let's now focus on the problem of learning our classifier scoring model. In general, classification is a family of supervised machine learning algorithms that identify which category an item belongs to, for example, whether a transaction is a fraud or not a fraud, based on labeled examples of known items, for example, transactions known to be fraud or not. Classification takes a set of data with known labels and predetermined features and learns how to label new records based on that information. Here's the code that I've written in Scala programming language that trains the classifier algorithm, evaluates its performance. What we're doing in here is applying random forest classifier algorithm, first using some hand-picked parameter values, and then building a more sophisticated pipeline that trains and evaluates several different parameterized models, and at the end of this process picks the best performing one. Let us now run the code that will train and select the best performing model and save it for future use in the scoring application. As we can see, by exploring different hyperparameter values of the model, we have improved its accuracy, which increased from around 60% to 73%, meaning that 73% of test samples were correctly classified. However, by looking at its additional evaluation metrics, precision and recall, we can see that accuracy of this model needs to be further refined before it goes into production. This can be achieved by identifying the most influential user features, further exploring model parameter space, and experimenting with other supervised learning algorithms. For brevity, we will stop at this stage and assume the model is good enough for applying into our real-time scoring scenario, but please be aware that fitting the good model is the most critical stage, as it determines the accuracy of our solution and should be perfected until satisfactory accuracy is achieved. The next stage in our project involves embedding the model in Spark application that will ingest real-time stream of credit scoring requests and then classify them into positive or negative cases. For this purpose, we used Apache Streaming component and coded our application's logic in the following way. The app continually accepts batches of inflowing requests, sends them to classifier algorithm, and returns the output to the output stream represented by a console. Console output could be easily substituted by a more elaborate output stream sending all labeled results to other external system. This step was omitted for brevity. The code of the core application looks as follows. We define a streaming context that will accept all streaming data in the form of 1 second batches. We then load our trained credit scoring model and hook it up the incoming stream with Flume event processing receiver. When scoring requests arrive, we iterate over them, extract features needed by scoring model, and request it to predict scoring labels. In the end, we output the data to the console. To demonstrate the whole process, let's run the simulation. Please note that Flume agent responsible for streaming data is already started. Let's now start the main credit scoring app, and before it starts, let's have a look at the Flume client application that will stream the credit scoring requests. In here, every 10 milliseconds, a new request event will be sent to Flume agent that will then reliably send it to our credit scoring application. Now that the Apache Spark app has started, we can initiate scoring request stream. As requests flow into our credit scoring system, we can see that it processes them and generates credit scoring predictions for individual requests. Prediction indicates that user should get a credit and 0 means he should not get it. As mentioned earlier, output from our scoring app could be also streamed in real time to external system, but this was omitted for brevity. The last thing we will look at is the performance of our solution. On the Apache Spark's management panel, we can see that it is able to process over 40 credit scoring requests per second, which is not bad considering we run it on a medium spec laptop and not the cluster. At this point, we have reached to the end of this blog. I hope you enjoyed it and understood the advantage that Apache Spark provides in building advanced analytical applications. Speak to you soon. Bye.